Hello everyone. Um, let's continue on cache memory. Yesterday we stopped at virtual memory, right? So what I think is, uh, mm, mm, let's say we have cache and CPU, and there is this main memory. So obviously this is larger. Let's say 4 GB, and this is some factors of KB, and this is CPU. So it is evident that not entire data of this main memory can be put into this cache memory. Only necessary few locations can be brought into this cache memory. So we have seen how this data is being fetched and what kind of data and how it is fetched, how it is mapped. Mapping is really important, and that is what I want to concentrate now. Why mapping? Like, um, it's best when you discuss it in terms of CPU. CPU generates an address which corresponds to main memory. Let's say this is 4 GB, right? 1 GB requires 2 power 30. Okay, 1 GB is around 2 power 30, and for 4, 2 square. So I need 32 lines of address to address 4 GB locations. So if I give these 32 lines to cache memory, and like CPU generates address in 32 lines. So if I directly access data from RAM main memory, it will take a lot of time, like access time is high. So that's why we have put a intermediate, kind of temporary storage, you would say, which is really close to CPU and even functions at the frequencies of mostly very close to CPU frequency. So, and here in cache we use usually SRAMs, right? These are less denser than main memory. These are basically DRAMs, and these are very costly, right? So we usually use fewer KBs of cache memory, and thus we cannot accommodate entire RAM, DRAM main memory locations into cache. So somehow we should use some mapping, address mapping, so that these locations, these addresses can be stored in specific locations of cache. Okay, that's clear. So similar thing applies to, mm, that secondary storage as well. So we have a secondary storage, secondary storage. This is hard disk basically, or hard drive, whatever way you wanna call. Or sometimes even we plug pen drives some SD cards. Those are IO things. Like we uh, give some input from external world through some interfaces. So basically, hard disk is installed on the motherboard and this main memory. Let me make it small so that hard disk looks bigger. So this main memory, again, this main memory resembles as cache memory, and this secondary storage, whatever that is, resembles as main memory in this context, in this above context. So now, let's say hard disk is around 256 GB and main memory is only 4 GB. So again, this has 32 lines of addresses and 4 GB locations, and this has 256 GB locations. So there is a difference of two, 1, 2, 3. Okay, there are extra 3 lines, right? 35 lines to this. You can even calculate for 1 GB it takes 30, and for 256 it takes around how many? I think it's around 8, right? 8. 2 per 8 is 256, so 38 lines, not 35. How would I arrive? Like, oh, I thought that it okay. So 38 lines are required for 256 GB, right? So, um, okay, this is 32 lines address, and this address is 38. So, but their like address comes from CPU. CPU generates address of 32 lines to access main memory, but I think we need to somehow generate this, what do we say, uh, actually this hard disk, hard drive, whatever secondary storage is called as virtual memory. Okay, this is virtual memory. We will get to know why this is called as virtual memory in uh, after reading a few pages. Let's see. So basically, CPU addresses with 32 lines to the main memory, but somehow main memory has to bring some chunks of data from virtual memory, secondary storage, which is having 38 lines of address that has 256 GB, like 256 giga locations. So how do you generate these many locations? What are those techniques? That will be discussed in this around, let's say, 5 to 6 pages or 5 pages, I guess. Let's see. This is interesting because for cache and main memory it is easy. For cache and main memory it is easy because whatever the possible locations are uh, there, like let's say it is 4 KB, so we'll be having some rows and we will be having some words like cache blocks. Okay, we will just use some address lines and the remaining address lines will be considered as tag. But here we are generating more locations, so it's actually only 4 GB, but we are kind of generating more space. We are kind of utilizing, mm, how do I put this? Actually, I have 4 GB, right? I have 4 GB, let's say LPDDR4 RAM, LPDDR5 RAM, anything 4 GB, let's say. So that is my physical memory. And the communication between CPU and main memory uh, is actually the, how do I say, like CPU addresses with 32 lines, which directly goes to main memory. Usually it should go to main memory because that is the storage area where there are entire instructions and data that are being currently run. Okay, and we have introduced some intermediate storage areas, those are caches, to improve the access time. Okay, so main communication is between CPU and main memory. Okay, so physically I have 4 GB, but it is having some backup secondary storage, let's say 256 GB. So it has some chunks of data here, blocks, correct? So it is kind of picking one block and it fetches into main memory like this. So whenever it wants another different data from the secondary storage, it would replace some chunks. So actually I have 32 lines of address, but this requires 38 lines. Then how would I generate address to this secondary storage and pick up this required chunk of memory and place it in main memory? So this is what uh, we call as virtual address. We have physical address generated by CPU, but we somehow create a virtual address that maps to secondary storage. Okay, I got to know what, like why this RAM is called physical memory and why the secondary storage is called as a virtual memory. So it's a, like, you need to always consider CPU. CPU is the main thing. CPU generates some lines of address, so it is aligned to main memory. So that is physical memory, and somehow physical memory is accessing more than 4 GB from the secondary storage by generating some virtual addresses. Okay, so in a way it is uh, like it is we are seeing an illusion that 4 GB main memory kind of able to access 256 GB storage, so it actually can possess 256 GB, but physically it has only 4 GB. Okay, this looks like Lotus looks something like this. Okay. Mm. Maybe let's guess how it is done. I too don't know. Let's see. Mm, mm, mm. Maybe we can do something like uh, Siri. Uh, just a second, guys. I'm just imagining things out. I have physical memory, which is main memory. Let's say that has 32 address lines, but this has, uh, let's say for simplicity, I have only 34 lines of uh, 34 lines addressable secondary storage. That in the sense, it's around 16 GB of secondary storage hard drive and 4 GB main memory. Hmm. So, okay, let's see in this way. Let me draw everything that comes to my mind. Let's say I have hard drive. I will fix something. Hard drive or hard disk. Hard disk. Okay, hard disk is having 16 GB. So for 16 I need 4 lines. For 1 GB I need 30 lines. So 34 lines of address. So in a way, this first location starts with 0. So since we have made this as a square, we'll split 34 lines equally. So 17 here and 17 here. Correct? 34 lines, 17, 34. Then it is like how this is equally distributed. Is this actually 34? For 30 is 6 GB. Mm, yeah, it's correct. Okay, maybe. mm, mm, mm. Let's say this has 16 lines, this has 16 lines. So 16 into 16. So this is around 64 KB. This is 64 KB. So 2 power 6, 2 power 6, 2 power 12. This is MB, and I'll get 4 GB. So here I have 4 GB, and here I have another 4 GB. Like actually, what's happening is I have 16 lines, okay, and above that, mm, let's put it in this way. I have a mux. Actually, it's not a mux, it's actually a demux. I have a demux. Here I have 16 lines. Here, same 16 lines. So, actually, 16 lines comes from here. So, there is one selection bit, that extra one address line. So, in total, I have 17 lines in column. and here I have another demux, 16 lines, 16 lines, 16 lines comes from row decoder, let's say, and there is a selection line 1 bit. So in total I have 17 address lines given to row. So 17, 17, 34. So I have 4 GB here, 4 GB here as well. So in total 16 GB. And so this is hard drive, right? Hard disk. So I need to think about main memory. Main memory has only 4 GB. 4 GB. So 4 GB requires 32 lines. So let's say it's a what we say, like every line contains 1 byte, such that there are 4 gigs of lines. I mean 4096 lines of 1 byte each. Let's say that for our simplicity. So 32 address lines will be given to row decoder only. Okay, we do scrambling, but for now assume that row decoder has 32 address lines. So this 32 address lines has to be mapped with this 34 lines. So how do I do this? Let's say currently I have mm, let's say currently mm, mm, I have this location. So I have mentioned that this location starts with 0 and it goes on. Since we have done scrambling, if it had been a straight line, it would have been easy. Let's see that case as well. Then we will come to this scrambling part. We have 4 GB, 4 GB, 4 GB. And again, address lines will change. That's different. So let's see this one only. I need so for like first of all I need to select row, which row and which column. So for that I need LSB of this 17 bits. This selection line has to be 0. For this it is 0 and this is 1, and for this it is 0 and for this it is 1. So let's say I have let's say I have this 17 lines which are going to row, and let's make it column, and I have another 17 lines that are going to row. So for this LSB of column has to be 0. Is it LSB or MSB? I think it's MSB, right? It has to be MSB. It's actually MSB, I guess. Yeah, it's actually MSB, because you like for 16 lines I can access 4 gigs of locations, like not 4 gigs of locations, 64 KB. So there will be 64 kilo locations in the horizontal line in this block, and 64 kilo locations in vertical block, vertical line in this block. So after reaching 64K, I need to uh, make the MSB as one and repeat another 64 kilo locations. So it's actually MSB. So my MSB, so this is 0, right? 0, and this is also 0. So, so these 16 lines will be directly mapped to main memory. There's no issue in that. So 16 lines map to direct uh, RAM main memory. One goes to row, one goes to column. Everything is fine. It makes 32. But I have these when I access data from secondary storage, it has extra 2 bits. So how do I generate exactly generate like I have generated 0 0 here, so I made these 2 bits as 0. Like if I want to access this, I need to make them 0. So how do I know that those MSBs are to be 0 so that I could access this? If uh, if the column MSB is 1, row MSB is 0, then I could access this one. So other cases as well. So how do I generate this? So this is translation. I studied this. I saw some terminology as translation of address. So how do I generate this? Maybe uh, I didn't check my audio. I think it's audible. Of course, there is some noise. I'm trying to figure it out. How do I reduce that? Man, how could we change this? So what we are doing is we are kind of, let's say I have this. Let's name this as uh, B0, B1, B2. Actually, this is B3, B3, B2. Okay. So if I like currently I have B0, but my RAM wants to have B1 block. So in a way, I'm just replacing B0 with B1. So there would be some replacement policies in this as well, maybe, so that the circuitry generates the address in such a way that these MSBs will change to access this one. So somehow we design the circuit to generate these bits. I heard some terminologies. I remember some terminologies from MPMC, microprocessor and microcontroller, that we have physical address and some offset address. So we kind of left shift and add the address. So okay, maybe this could be possible that we left shift the address lines of this and then add some data or something sort of that. I want to figure this out on my own, but I'm exactly not getting the intuition how it is done. Mhm. It takes time, but mm, we can. I think we can figure it out on our own. This is paging concept actually. These are pages, and I'm accessing some pages. So how do I access? How do I generate this address to access a desired page? Hmm. Mm. 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 So CPU asks for a address or some data. No, it's not actually related to CPU. Like CPU knows that there is only main memory, so it actually asks that 32 addressed lines locations. So it doesn't know about the secondary storage. We are just uh, making this, creating this illusion that we can access more data. Virtual memory. So maybe I can left shift this address bits and add some. I don't know. Excuse me. Maybe instead of left shift, I think we need to right shift. Let's say I have 32 bits of data. Uh, I have sent this to a 34 register, 34 bit register. This is 32 bit register. So in a way, I have occupied. Let's say you have entered those 32 bits in more significant bits, and you have right shifted that, and now you have empty 2 bits in the MSB, and you have occupied 32 bits. Now it is someone's responsibility to appoint some appropriate bits to these two locations, so that actual page, like desired page, is selected. Desired block in the secondary storage is selected. Let's see. So of uh, it's enough that we have studied all these on our own. We got some intuition. 1 minute. Am I audible? Like it could, I think noise might have reduced. It should be audible well now. Or should I improve a bit? If I increase this, no, then there will be that noise will not that much reduced. Like it picks up noise easily. I should think of adding some filters. We'll see. Someone will help me out. I turned off my fans actually. Yeah, most modern systems use a hard disk, also called as hard drive. We studied this yesterday, right? Hard disk is the lead. Okay. The objective of adding hard disk, okay, is to inspect. Okay. We studied all these things. Programs can access data anywhere in virtual memory. Okay, so they must use virtual address. Okay, so that is what we are discussing. Like program currently, let's say I have some data and I want to have some data in this block or entire block. Then I have to generate some virtual address to access this secondary storage to get our desired data, chunk of data or entire block into the main memory. So for that, I need to generate virtual address from this physical address. I have physical address which has come from CPU. I need to generate some virtual address to access secondary storage that specify the location in virtual memory. The physical memory holds a subset of most recently accessed virtual memory. Yeah, same concept. Like main memory acts as a cache and secondary storage acts as a main memory. This physical memory holds a subset of most recently accessed virtual memory. In this way, physical memory acts as a cache for virtual memory. Thus, most accesses fit in physical memory. But cache and main memory we have used like, mm, okay, this is different. We cannot relate, like, when it comes to addressing, we cannot relate to cache and main memory because main memory can be addressed because of the CPU. That CPU addresses exactly uh, exactly these many number of lines that can be mapped to main memory. But here the case is different. We are lacking some address lines. Okay. Yeah, thus most accesses hit in physical memory at the speed of DRAM. Yet the program enjoys the capacity of larger virtual memory. Okay, virtual memory systems use different technology like terminologies for the same caching principles discussed in 8.3, 8.4. Okay, where is 8.3? Okay, like in cache we have terminologies like set associativity, we have number of ways, block size, like number of blocks, cache blocks, direct map, like how the address is mapped, all these things. Okay. Summarizes the analogous terms. Okay. Okay. So the like it's not really exactly similar to cache and main memory. Relation between cache and main memory cannot be directly linked to main memory and that secondary storage, because address lines का issue आ जाता है. We have this issue of addressing, so we have different terminologies now. So for cache we have block. So in cache we access one block, one cache line, not exactly entire cache line. It might have some blocks in it. So block is mapped to, like, terminology is mapped to page. Block size. Okay, we in cache we have single line. Cache line is called as block. Entire line. I told you wrongly just previously. I told you something that is wrong. Entire cache line, entire cache row is called as block. Okay, and number of blocks is number of rows in cache. So block is mapped to page. Block size, like how many bytes, like how many words are there in the cache block, is page size. Block offset. Block offset is something that if you have multiple words in one block, in one cache line, then you have some block offset to address those individual words in the block itself. So this is page offset. Miss. If there is a miss, what do we say? Like cache miss. When you try to access data in cache, there is a miss. We say miss. And here, when you try to access some data in virtual, kind of, let's say, in main memory. Main memory, okay, wait. Main memory is seeking some data from virtual memory, which is secondary memory. Okay, if the secondary memory doesn't have that data, then it's a page fault. Okay, we are searching for a page. Main memory is searching for a page, and that page is actually not there in secondary storage. So there is a page fault, something like that. Or it is searching something uh, in main memory and it's not there, then there is a page fault. Then you go to the secondary storage and fetch that desired data. Let's see. Tag is used in cache to verify whether the data actually has associated address within it. Like cache memory doesn't actually store only data, it actually stores its uh, address as well. So while the CPU addresses some location, we'll just compare both tag and that address. If those matches, we'll just make it a hit and we'll just fetch it. Here we have virtual page number. So we have page numbers. If the page numbers are matched, then that's a hit. We'll see what is page fault. And I got some doubt regarding block offset, whether uh, whether it is correct what I have thought. Here I have block offset as if there are multiple words in a block, then we need block offset to access individual words. Correct. So In an analogous virtual memory system, mhm, each physical page, each physical page would need a comparator to check the most significant virtual address bits against the tag to determine whether the virtual page maps to physical page. Okay, there are some tags for mm, uh, data that are present in secondary storage. So when I try to access that particular page or some data in the secondary storage, those will be cross-checked, or is it virtual memory? Okay, maybe hard disk contains those. Let's see. What I interpret is, my interpretation is, this is virtual address, man. This is virtual address. So I have, let's say, 34 lines. 34 lines of virtual address. So you have some pages in a secondary storage, and each location, like each address, has some tags associated with it. Okay, I think I got this. Like each address is 34 bits. So 32 are for, like 32 are common for each and every block, and other 2 bits will determine which block that the data will go. So I think these are tags. So these will be cross-checked with this virtual address. Then how do we even generate this virtual address? Actually, we have these 32 bits and we need to generate these 2 bits extra. Let's see. A realistic virtual memory system, okay, has so many physical pages that providing a comparator for each page would be excessively expensive. Okay, instead, virtual memory system uses a page table to perform address translation. So instead of comparing things, we use a table of data that does address translation. A page table contains an entry for each virtual page. Okay, each virtual page's entry is there in the table. Okay, indicating its location in physical memory. Acha, okay, or that it is not, it is on the disk. Each load or store instruction requires a page table access followed by a physical memory access. The page table access translates the virtual address used by the program to a physical address. The physical address is then used to actually read or write the data. Okay. The page table is usually so large that it is located in physical memory. Hence, each load or store involves 2 physical memory accesses. A page table access or data access. To speed up address translation, translation look aside buffer TLB. Translation look aside buffer. Caches are the most commonly used page table entries. The remainder of this selection, like section subreddits, as translation tables and TLBs. Okay. Lot of stuff. In an analogous virtual memory system, each physical page would be like comparative. Okay, a realistic virtual memory system has so many pages that providing a comparative for each page would be excessively expensive. Okay, we use page tables, and to speed up address translation, we use translation look aside buffer caches. Okay, the most commonly used page table entries because caches are faster, they are made out of SRAMs. The remainder of this section elaborates on address translation, page tables, and TLBs. Address translation. In a system with virtual memory, programs use virtual addresses so that they can access a large memory. The computer must uh, translate these virtual addresses to either find the address in physical memory, yeah, like when it comes from physical memory to wait, the, the computer must translate this virtual address to okay, when the data is coming from virtual memory to physical memory, then it has to be translated to physical memory address. Or take a page fault and fetch the data from hard disk. Yeah, wait, I got confused. The computer must translate these virtual addresses to either find the address in physical memory or take a page fault and fetch mm, data from the hard disk. Huh. We'll see. We'll come to this statement again. Recall that virtual memory and physical memory are divided into pages. Okay. Uh, okay. The most significant bits of the virtual or physical address specify the virtual or physical page number. The least significant bits specify the word within the page and are called page offset. Okay, so this is physical memory. It's going from I have around 32 bits, correct? Other ones 0 to 1. Okay, maybe it's actually 31 bits to power 31, which is 1 to 2 GB. So 2 gigs of locations, and these are mapped to some locations in virtual memory. So figure 8.21 illustrates page organization of a virtual memory uh, system with 2 GB of virtual memory and 128 MB of physical memory. Okay, 2 GB actually this one. Okay. Uh-huh. Actually, this is 2 GB and this is 128. Hmm. Okay. We have a virtual memory of 2 GB. Let's write it down, or else I'll get confused. 2 GB of virtual memory, and I have physical memory of 128 MB. So 128 MB is nothing but 2 power 20, 2 power 5, 6, 7, right? 27. And this can be divided into, he has divided that into pages. Okay, each 4K page. So each page is 4K. 4K is nothing but 2 power 11. Correct? Power 11. No, 2 power 12. So 2 power 27, 2 power 12. I'll get 2 power 15. So around how many pages? 32 kilo pages. Oh my god. These many pages are there. MIPS accommodates 32-bit address with 2 GB virtual memory. With a 2 GB virtual memory, only the least significant 31 virtual address bits are used. The 32nd bit is always 0. Similarly, with a 128 MB, 27 byte at 27 byte physical memory. You got 27 byte physical memory. Only the least significant 27 physical address bits are used. For 5 bits are 8, 9, 10, 8, 9, 10, 11, 2, 7. Only least significant. The upper 5 bits are always. Actually, for 2 GB, I need how many lines? 2 into 2 power 30. So that will be 2 power 31 lines. So here they have mentioned that with that 128 MB, 2 power 27 byte physical memory, 27 address lines, only least significant 27 physical address bits are used. The upper 5 bits are always 0. Actually, I need 4 only. Let's see. 8, 9, 10, 11. Because the page size is 4 KB, which is 2 power 12, which I have mentioned already, there are 2 power 19 physical page numbers. 2 power 19 virtual pages and 2 power 15 physical pages. Okay, I mentioned 2 power 15 physical pages. Okay, this will be around 19 virtual pages, 2 power 19 virtual pages. So the virtual and physical page numbers are 19 and 15 bits respectively. Okay, physical memory can only hold up to 1/16th of the virtual pages at any given time. The rest of the virtual pages are kept on the disk. Correct? 8.21 shows virtual page 5 mapping to physical page 1. Okay, they're mentioning this page 5 is is mapping to page 1 here of the physical memory. Virtual page 7 triple FC. Okay. Yeah, this one maps to page 7 double FE. And so forth. For example, virtual address an offset of 3 of 8 within virtual page 5. Thirteen F8. Okay. An offset of 3 F8. Okay. Mm. And specify the page. So I got some idea, but not exactly. I'm not sure that this is exactly what is working here. Only the page number needs to be translated to obtain the physical address from the virtual address. Translation of virtual address to physical address. Okay. Recall that virtual memory and physical memory are divided into pages. The most significant bits of the virtual or physical address specify the virtual or physical page number. Okay, there are two different addresses, and MSB in those addresses specify page number. लिख लेते हैं. So you have, let's say, physical address, and MSB specifies page number, and this is virtual address. This also specifies page number. The least significant bits. Let me reduce my screen brightness. Least LSB bits are that specify word within the page and called offset. Okay, so these uh, LSB will specify offset, right? Page offset. Words in page. So that is page offset. Like we have block offset, similarly with page offset is there. Page organization of virtual memory with virtual memory system with 2 GB of virtual memory and 128 of physical memory. Okay. Okay. So here I have from 0 to triple F, double 0 to F. Okay. Okay, let's see. There is some context in it. So actually physical memory is divided into 4 KB pages, like 4 KB pages, like each page is 4 kilobyte, right? So in that way, if I have a physical memory of 128 MB, it requires this is 7 plus 27 lines. And if you have a secondary storage, that is virtual memory of 2 GB, you will require, this is 31 lines. So each page, so there are pages in this physical memory, and each page is 4 KB. So number of pages will be total size 4 KB. So I'll get around 64, 32 KB actually. Okay, excuse me. MIPS accommodates 32-bit address. Uh, okay, actually we have 32-bit addresses. Okay, so write that somewhere. We'll highlight that. MIPS is 32-bit address lines. It has 32-bit address lines. With a 2 GB 2 power 31 byte virtual memory, only the least significant 31 virtual address bits are used. Okay, the 32nd bit is always 0. Okay, since I require 31 lines, these 31 lines will be uh, utilized to access the virtual memory, and this will be 0. This 31st. Okay, we'll just move this. So MSB will be 0. And similarly, with a 128 MB 27 byte physical memory, correct? Here you have 27 and only the least significant 27. Okay, in total I have 32, so I'll be leaving 5 bits. So those will be 0. So I have 27 lines, so I need 27 bits, and these 1 2 3 1 2 3 4 5 bits are 0. Okay, because the page size is 4 KB. Okay, there are, so since we have pages in virtual memory and physical memory, uh we'll just try to know how many pages are there. So we already calculated, it turned out to be 32K locations. So because of page size is 4 KB, 2 part 12 bytes, there are okay, actually 4K pages. Okay, both the physical and virtual memory are divided into pages. Okay, 12, and I have 2 power 19 virtual pages and 2 power 15. 2 power 15 is nothing but 32 kilo. Okay, thus virtual and physical page numbers are 19 and 15 bits respectively. Physical memory can hold up to wait 15 bits. 20, okay. Physical memory can hold up to 1/16th of virtual pages. Why? Because there are more extra bits for virtual memory, like 16 pages uh, for a one page of physical memory. There will be 16 pages of virtual memory. So that is what he is mentioning. Physical memory can hold up to 1/16th of virtual pages at any given point. So if you have mm, some pages that have offset same as like offset in the virtual address and offset in physical address are same, but the MSBs will differ accordingly. And among 16 pages of virtual memory, one page can be taken by the physical memory. So it can hold up to 1/16th of virtual page, because if you try to access another page of same what would we say, same offset address, then there will be some conflicts. So we need to go for levels of pages, I guess. We'll see. Shows virtual page 5 mapping to physical page 1. Yep, physical page 1, virtual page 5. FFC. For example, virtual address 53F8 are offset of 3F8. Virtual page 07 triple FC triple FC. Okay, that one. Okay, okay. So within virtual page 5. Maps to why it is virtual page 5. So maps to physical address 013F8. An offset of 03F8 within physical page 1 the least significant 12 bits of the virtual and physical address are the same, and specify page offset within the virtual and physical pages. Page offset within the virtual and physical pages. Only the page number needs to be translated. Wait. So least significant 12 bits of the virtual and physical address are same, and specify the page offset within the virtual and physical pages. Okay. Only the page number needs to be translated to obtain the physical address from the virtual address. That will be least significant bits indicate the page offset and require no translation. The upper 19 bits of the virtual address specify virtual page number. Okay, and are translated to a 15-bit physical address, physical page number. Okay, the next two sections of page tables. All this is address translation. Page table. Okay, let's write anything. Let's write everything, or else I'll just get sleepy. So, how many pages are there in physical memory? Uh, there are 4 KB, right? 4 KB pages. Like each page is 4 KB, and here 4 KB page. So, this relation has to be satisfied or what? Number like page size has to be same for both physical and virtual memory. Because the page size is 4 KB, 2 power 12 bytes, there are 2 power 19 virtual pages. So 2 power 27 by 4 KB is, okay, here I wrote that already. Physical pages 2 power 10 515, and virtual pages equals to 2 power 31 divided by 12, that is 19. So there is a difference of 4 bits. So this requires 19 bits and this requires 15 bits. Okay. Physical memory can hold up to 1/16th of virtual pages at any given time. Alright, physical 1/16th of virtual pages. Okay, there are 2 power 19 pages and 2 power 15 pages respectively. So physical memory can have 2 power 15 pages in any given point of time. So if we relate that with virtual pages, it will be 1/16th. Okay. The rest of virtual pages are kept on disk. Okay, fine. 8.21. Pure virtual page 5 mapping to physical page 1. Virtual page 5 mapping to physical page 1. Physical page 1, this one, 0 to triple F, triple F. Okay. This one or what? wait, uh, virtual page 5 mapping to physical page 1. Okay, page 5 mapping to page 1. How? 3 zeros. Cha, cool. Okay. We can put this in this way, like I need to elaborate this. Mm, If you have large hard disk and you have pages and so on, and you have this main memory, which is physical memory. Mm, it can have up to 2 power 15 pages. So if I start indexing the page numbers, this will be 0, this will be 1, and there will be what 15 addressing bits, right? So if I write this in hexadecimal, 0 0, it will complete 12, and now this will be 0 0 0 0. So like that I can go up to f f f. I'll be left with 3 bits, so that will be 7. So again 7 f f e. So I have these many pages in physical memory, but in main memory, like not main memory, sorry, secondary memory, I have 2 power 19 pages. So this will be I'll shift this aside as small area so that I can write the locations. So this will be 0 0 0 0. I'll get 16 and remaining 3. Okay, 0. So 1 0 0 0 0. Like that I'll go up to f f f f 7 7 f f f e. Okay, so here I can map since I have a physical address of physical address is 1 0 0 3 MSBs. These are 4 bits, 4 bits, 4 bits. In total I have 15 bits. So this is physical address. And in virtual address I have 3 bits as 0, 4 bits, 4 bits, 4 bits. Let's say if I need to map this with some page in the virtual memory, then this has to be 0001. These are 4 bits. These 4 bits are also 0. These, let's say 0, 0, 4 bits. These are MSB 3 bits. So if I want to map, I can map this, and even I can map other address as well. Let's say this is 0, 0, 0. Let's make this as mm, 5, 0, 0, 0, 1. This also can be mapped, right? Wait, 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 wait. I got confused. Actually, this is easy, but I'm not that focused now to write everything clearly. That is page number. So each page contains 4 kilobytes. So they have to be byte addressable. So I'll have some locations as well. Even if they're not even byte addressable, they have some location, right? Let me write those things. 0x. These are 19 bits, right? So 3. Here I have 4, 4, 4, 2, 0x. I can go up to, if I need 4 KB locations, 4 kilo, I need 12 bits. 12 bits in the sense 3 LSB bits of a hexadecimal representation. So F, 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 and 0, 0. Correct? Hmm. Yeah, you can get out. So the next page, like page 1 starts with 0, 0. These are actually 7 zeros. So it has to be 1, right? So 1, 0, 0, 0, 2, 0x, 0, 1, F, 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 something like that. Correct? So if I go on write this, I'll go to 2, 2, 2, F, 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 then 3, then 4, then 5, and this goes on. And here, if I write down, oh my god, So I can go from, these are 15 bits. Hmm. Um, I need 4 kilo location again 12. So F F F 20x 1 triple 0 0x 1 F, such that I have, hmm, yeah, okay, actual address is, 27, right? I also forgot a, very bad. What had happened is, so here I have how many lines? 31 lines. Okay. So here I have 31 lines of address. First one will be like first MSB will be 0 always. So 0 x, there will be around how many? 8 hexadecimal, like hexa bits. So 0 0 0 0 1 2 3 4, 8 zeros. So it go up to 4 kilo, right? I need 12. So okay, 0 0 0 0 F F F. These are actually 5. Mhm. Now it goes to 0 0 0 0 1 triple 0 x 0 0 0 0 1 triple, something like that. Okay. Now this can be mapped to, here I have how many lines? 27, right? I have 27 lines. Actually it is 32. Actually it is 32, so 5 bits will be 0. So 0x 0 0 0 0 0 0 0 0 0 0. 0 f f f 0x 0 0 0 0 1 double 1 triple 0. Hmm. Uh, Actually, I think these two can be mapped, right? Let's see why it is mapped to this one. Um, Shows virtual page mapping, page 5 mapping to physical page 1, virtual page FFC 5, 5 in the sense, no, 1 triple 0, 1 triple 0. Hmm. Actually, I can write this as 0x 4 zeros, binary. I want to write this in binary 0 1 0 1 and then again triple 0. So actually, this thing 4 4, yeah, 1 12 zeros, 1 12 zeros. Yeah, this is the same thing, 1 12 zeros, 1 12 zeros. So these two map together. But actually, the uh, page number that varies actually. So since 4 KB is the page size, we ignore the least 3, at least 12 bits. And then from 13th bit, we consider. So thus the first page and fifth page can be mapped, and even first page in physical and first page in virtual can also be mapped. Okay, and if you go even further, you could even have a different number, say 0x, oh my god, 0x 0 0 0 0. These are hexadecimal and this is binary 0 1 1 1. Okay, is a hexa. So this also can be mapped to first page of physical memory. So this is what 7. So seventh page of am I correct? Yeah, seventh page of virtual memory can also be mapped to first page of physical memory. So something like that. So virtual page 7FFFC mapping to physical page 7FFE, virtual page 7FFFC, okay, 7 triple FC. Um, yep, like there are 19 to 19 pages, so we need 19 bits to address them. So triple FC will contribute to 16 bits and 7 is 3 bits. That is the thing. And shows that virtual page 70% backlink, and so forth. C is 1100. E is 14, right? 14 in the sense 1110. Okay. Oh, it is map. Mm. 0 triple one F F E is timber 14 8 12 is 0, and then we have extra 0 is map button is map button 0 x triple one F F triple F. What is this? Okay, we should leave 3 bits, right? So triple F C 7 double F E. Hmm. So I shouldn't consider this. I mean, let me write that as it is. Triple F C is 100 triple 0. So I would consider only these. Like this is a 4 KB, and this is my page number, right? This is 14, isn't it? 0 1 2 3 14, and this is 12, right? This map. So we are just looking for offset address. Then in that sense, everything will align. No, though it's not correct. So for example, virtual address 53F8, an offset of 3F8 within virtual page 5 maps to physical address 13F8, an offset of 3F8 within the physical page 1. These significant orbits of the virtual are the same, and specify the page offset within the virtual address. Only page number needs to be translated to obtain the physical address. Virtual address, okay. Mm-hmm. Like there will be around how many pages? 2 power 15 pages, 2 power 19 pages. So 4 KB each. Now I think I'm getting some clear picture. Mhm. There will be a lot of conflicts in this. So illustrates the translation of virtual address to a physical address at least 12 bits in page offset. The upper 19 bits of the virtual address specify virtual page number in bit page number. These are 12 bits as it is, and then the other 5 or 7 bits and then these things. Okay. Mm, 16. Find the physical address of virtual address 247C. 47C is offset using the virtual memory 8.21. 47C. Remaining 19 bits of the virtual address give the virtual page number. So the virtual address is found in virtual page 2. Virtual page 2 maps to physical page of 7 triple F plus virtual address to physical address. Okay, pages are being mapped. Okay. So it's not like you randomly place each page in a secondary storage. Sorry, it's not like we randomly place anything from the secondary storage. We just pick some page from secondary storage and we place that in primary memory, main memory, that is physical memory, uh, anywhere. Like it's not like we shouldn't place in a specific place. It can be placed in anything. So this is a wrong assumption that I thought. Actually, primary memory, physical memory, main memory has some fixed pages relating to the secondary storage. Like if I want to bring um, one page from secondary memory, then it will go to a specific page in main memory. It cannot go wherever it wants. Okay, so I thought I got this analogy, right? Main memory acts as a cache and secondary memory acts as a main memory. So while relating that, I thought there would be some replacement policies in this as well. It's not like that. This is fixed. So it's like a LUT, lookup table. There will be some fixed values, fixed value outputs for the given inputs. So if I give one virtual page number, it will map to one physical page number. But one physical page will map to 16 pages in virtual memory. That's for sure because virtual memory is big. It has to map to more than one page. And there is this relation that virtual memory contains 2 per 19 pages and physical memory contains 2 per 15 pages. So there is a difference of 2 power 4, that is 16 pages. So one page of physical memory has to map to 16 pages of virtual memory. Hmm. So page number 5. Let's see. The processor uses a page table to translate virtual addresses to physical addresses. Recall that page table contains an entry for each virtual page. This entry contains a physical page number and a valid bit. If the valid bit is 1, the virtual page maps to physical page specified in the entry. Otherwise, virtual page is found on disk. Wait. He's telling what I'm thinking right in my mind right now. The processor uses a page table translation. Recall that the page table contains an entry for each virtual page. This entry contains a physical page number and a valid bit. If the valid bit is 1, virtual page maps to physical page specified in the entry. Otherwise, the virtual page is found on disk. Okay. Then I need to go back to the disk and bring the data again or what? Because page table is so large and it is stored in physical memory. Let us assume for now that it is stored as a contiguous array as shown in 8.23. The page table contains the mapping of memory memory system of figure 8.21. Mm-hmm. The page table is indexed with virtual page number. For example, entry 5 specifies that virtual page 5 maps to virtual page 5 maps to virtual page 1. Okay, entry 6 is valid, p equals to 0, invalid, sorry. So virtual page 6 is located on this. Mm-hmm. This thing. Use the page table to perform address translation. Virtual page number is 2. Okay. So 0, 1, 2. Okay. So how do we decide that whether this okay, there is a hitman. So we somehow create these valid bits according to the selected virtual page number. If I want specific, like out of 16, if I get the desired virtual page selected, then I'll make this valid bit higher, else I'll make this 0. Something like that. The page table can be stored anywhere in physical memory at the discretion of the OS. Okay, it's an OS thing. If the OS selects the correct page, it makes the valid bit 1. So in a way, only after selecting the correct page from the disk, OS makes the valid bit high. The page table can be stored anywhere in physical memory at the discretion of the OS. The processor typically uses a dedicated register called the page table register to store the base address of page table in physical memory. To perform a load or store, processor must first translate the virtual address to a physical address and then access the data at that physical address. The processor extracts the virtual page number from virtual address and adds it to the page table uh, register to find the physical address. The processor then reads this page table entry from physical memory to update physical page number. If the entry is valid, okay, it merges with physical page number. It page also to create a physical address. Finally, it reads or writes data physical address. Because the page table is stored in physical memory, each load store inverse to physical memory access. Mm-hmm. Translation literacy. Virtual memory would have a severe performance impact if it required page table read on every load or store, doubling the delays of loads and stores. Um, Fortunately, page table accesses have great temporal and spatial locality of data accesses, and the large page size mean that the many consecutive loads or stores are likely to reference the same page. Therefore, if the processor remembers the last page table entry that it read, Uh, okay, okay, page tables. Hmm. Then I might have 16 different page tables, right? The temporal and spatial locality of data access and large mean that many in general process can keep large several page table entries in a small cache called translation look aside buffer. The processor looks aside to find the translation in the TLB before having to access page table in physical memory. In real programs, the vast majority of access is in the TLB, providing time-consuming page table reads from physical memory. A TLB is organized as a fully associative cache and typically holds 16 to 512 entries. Each TLB entry holds a virtual page number and its corresponding physical page number. The TLB is accessed using virtual page number. TLB hits, it returns corresponding physical page number. Otherwise, processor must read the page table in physical memory. TLB is designed to be small enough that it will be accessible from one side. TLBs typically have a rate of greater than 99%. TLB decreases the number of memory accesses required or most load or 2 to 1. Consider virtual memory system is a two-entry TLB. This is a bit difficult to understand for me, at least.